Oh my god. That was an actually terrifying dream. The way that even happened was.
Hello?
It's probably nothing. What time is it? One in the morning. Damn, is summer already here? Feels like school went by so fast. It's like my life's going in one direction for 1,000 miles per hour, and I just don't know my navigation. It's like I don't know the magnitude of the situation until it actually hits me. Well, that's just... So like a vector? Yeah, like a vector. Oh my god! Who the hell are you? Oh yeah, I'm the life devil. I'm the guy who comes around when you don't understand your life vector. What? Exactly, and I'm the one who's going to teach you how to use it. Okay. You see, a vector is something that has both magnitude and direction. An example of this is your car. Let's say you're going 100 kilometers per hour east. A vector is usually represented by an arrow. In your case, you don't know what your direction is, and you don't know what your magnitude is until it actually hits you. Then what should I do? Well, I guess you could try plotting life a Cartesian vector. It's made of two things. It's made of a position vector and a coordinate vector. We use the position vector, we represent it in square brackets, and a coordinate vector using circle brackets. A is for x and B is for y. If we wanted to represent these components, we would use I and j. I being for A and A being for x, and j being for B and B being for y. For example, let's use the vector 3, 4. When writing that and representing that vector with its components, we get 3i plus 4j. That is a Cartesian vector. Okay, then I can try plotting my life like that. Well, that's thinking two-dimensionally. In life, you want to think three-dimensionally, which is not much harder since you really just add an extra axis, that being the z-axis. And you're adding extra terms c and k when you're drawing the components of that vector in three-dimensional space. And when expressing this vector, we get ai plus bj plus ck. That being the components of a three-dimensional vector, three-dimensional Cartesian vector. Also, your life vector is not going to be in one place the entire time. It's going to be constantly moving and going somewhere else, subtracting and adding to itself, multiplying and dividing it by itself. So you're going to have to keep track of it in some sort of way. How am I going to do that? Well, if you want to know the magnitude for life vector in both 2D and 3D, you can take its coordinates, square them, take the sum of them, and then take the square root of the sum to get its magnitude. We can also divide the vector into its horizontal and vertical components. This works for geometric vectors. What this means is that we're taking its vertical and horizontal components and using it to find the main component of the entire vector. Or we can use the main component to find the vertical and horizontal. To find the horizontal component, we can simply take the angle at which the geometric vector makes and take the cosine of it and times it by its magnitude. To find its vertical, we can do the same thing, except take the sine of the angle and times it by its magnitude. When adding two vectors together, we consider the direction where they're headed. Let's say you have two parallel vectors. They can either be in the same direction or opposite direction. What really matters is which direction they are going. If they're in the same direction, we simply add them, the direction doesn't change. But if they're opposite direction, that means that it's going to change direction depending on which one has the greater magnitude. Let's say you have u and v, and v is equal to 20 and u is equal to 40. Now let's say u is in the opposite direction of v. That means that the direction at which u is going to be favored in the resultant vector that happens when you add them together. This makes sense. When subtracting vectors, we simply just change the sign from positive to negative so we can efficiently add the negative vector to the positive vector. This being equivalent to just taking the positive vector and minus it from the other vector. So just be careful of the type of vectors you let into your life. What? When subtracting Cartesian vectors, we simply treat their components as like terms. And the product of x, y, or z will be the new coordinates for the new vector. When adding and subtracting geometric vectors, we can simply group their components, or we can take their magnitudes, plot them on a compass, and use trigonometry to determine the resultant vector of their addition or subtraction. This scalar multiplication is such that the vector's magnitude is only being affected, but not its direction. A scalar is something with only magnitude, so it would make sense if it only affected the magnitude of the vector. An example of this in real life is, let's say, your car. Let's say you're on the highway driving at 100 kilometers per hour, and you see a road sign that says you should increase to 300 kilometers per hour. In that case, the scalar multiple of that vector would be 3. When doing a scalar multiplication of a Cartesian vector, you simply carry out the scalar through every single one of the components, that being 3 times x, 3 times y, or if it's a 3D, then it would be 3 times z as well. And that would give you the new component, the new vector of your Cartesian. The dot product is taking 2 vectors and multiplying them together to create a scalar, which is just magnitude and not direction. When doing the dot product of a geometric vector, we take 2 vectors' magnitude and times them by the cos of the angle between them. When multiplying a Cartesian vector, we take the components xy or xyz, multiplying them together and add them together to get its magnitude. If the dot product of 2 vectors is 0, that means the 2 vectors are perpendicular.
But sometimes things in my life aren't always meant to be.
Yeah, pretty much. The cross product is a little bit different from the dot product. Instead of taking 2 vectors and getting a scalar, we take 2 vectors and get a new vector that is both perpendicular to both the other 2 vectors multiplied together. When doing the cross product for geometric vectors, we simply take the magnitude of the 2 vectors times the sine of the angle between them. We only use the cross product when we're doing 3-dimensional Cartesian vectors, and we use this operation to determine the resultant vector when using a cross product between 2 other vectors.
Some things in my life create new paths that I didn't know I could take.
Yep. Next is projection. You can think of projection as a shadow. Let's say we have 2 vectors, u and v. The projection of v on u is simply the component of v that is in the same direction as u. But that's only if the angle between them is less than 90 degrees. If the angle between them is more than 90 degrees, then the projection of v on u component would be in the opposite direction of which u's component is.
So some parts of my life can either be in the same direction as others or in the opposite direction.
Most definitely. Although they seem different, they are a lot closer to the same thing and boil down to one thing. One, a line needs 2 things: a position vector and a direction vector. The position vector is a point on the line in the equation. The direction vector is a vector that is directly parallel to the line that we are calculating that is represented by the equation. We could represent the 2D equation like this, and we could represent the 3D equation like this, where r is a general position vector on the line, r naught is the point on the line that we use to calculate any point on the line, m is the direction vector, and t is the scalar multiple of the direction vector. To find the direction vector, we can simply take 2 points on the line, find their difference, and that will give us a vector directly parallel to the equation. Then there are paramecic equations. Paramecic equations are simply equations that break down the equation of the line into its simplest form, that being x naught plus tx, or y naught plus ty. Or if it's a 3D plane, then you have z naught plus tz. This helps us determine any point on the line if it exists there or not. R squared equations don't have z components in their position. Well, R squared lines don't have z components in their vector or paramecic equations. And R squared equations only describe lines in 2-dimensional space, where 3 cubed lines describe things in 3-dimensional spaces, and where we can describe their motion and their direction and position much differently. Just remember, what matters is the position you want to be in and the direction it will take for you to get there.
What if I can't change my direction?
Start walking. What if I end up in a position that I'm not proud of and there's always a chance to change it? Just don't let that vector control the magnitude and direction of your life.
Yeah. I won't.
Good, now wake up.
What?
Wake up!